Okay, and
last forever ago, we saw the idea of using power series to solve linear ODEs. So basically the idea was we assume our y is equal to some power series centered at x naught. That is absolutely convergent. With degrees of convergence. I think they usually use rho. So we need absolute convergence because we want to be able to differentiate the series, and we need absolute convergence so that we know what we're differentiating. And we remember the rearrangement theorem that says if a series is convergent but not absolutely convergent, you can actually rearrange the terms to get whatever you want. That was a problem. We need to know what we're looking at and know, okay, this is a function, this is derivative, there's no ambiguity. So we needed absolute convergence, and we can find that in the radius of convergence using the ratio test, which you would have learned in Calc 2 or Calc 3, depending on where you learned it. I also want to know, and we'll talk about this, but we can find P using rho, using the ratio test. What y is determined. But it turns out the ODE itself will give you an upper bound. I'll talk specifically about how it will give us that upper bound. So we basically pretend there is a series out there, a power series, specifically a series of this form, kind of looks like an infinite polynomial centered at a certain point, that will solve the ODE that I'm looking at. And basically what we do is we differentiate it several times, we plug into the ODE, and then we kind of basically figure out a way to solve for these coefficients. Once we have those coefficients, I can say, this is the power series that solves it. Then we can check if it converges and if it actually makes sense to be the solution afterwards. But we can initially just jump in and just get our hands dirty and try to compute the series that will work. Now, in our attempts to do that, we made note that we were allowed to do several operations. Also recall absolute convergence means we could differentiate the sum. By the way, we can also integrate, although we're never really going to find a use for that here. We can differentiate the sum term by term. And namely, y prime would look like infinity. We also saw that starting at 0, once we differentiated this particular kind of power series, was optional. We could, n equals 0 is okay. Also here, n equals 0 is okay. We just bump it up every time we take a derivative because it's kind of superfluous to say what it is for n equals 0, because notice that there's an n here. If I put in n equals 0, I'm just adding 0. It's not going to matter, so I can just ignore the 0 term and start at the first term. Similarly here, the 0 term is going to give me a 0, the 1th term is going to give me a 0, so I might as well start from the 2nd term, and so on and so forth. So when I differentiate, I can bump these things up, but I differentiate term by term. I essentially look at it as if it were a polynomial. So do the power rule. And so that was one thing that we noticed we could use to our advantage. Another thing that we noticed, we could shift. So, i.e., if I have the series that looks like a n x minus x naught to the n, and say my n starts at some number a and goes off to infinity. We can shift n and move them to n plus some other number, and the series will also shift into, so I would replace all n's with n plus k's, and so this would be a minus k is what this would start at, going off to infinity, and then here I would have this n goes to n plus k, and that n goes to n plus k. And that's convenient because a lot of times I'm going to want to change the powers to be the same thing. So when I take the derivatives, I'm going to affect the powers. I want to be able to shift them back to the nth power, that way I can combine all the series, combine like terms. So being able to shift is going to be important. And it's known that these two series will actually output the same points. If you actually write them out, you'll get the same series eventually.
So coincidentally, in the example we used in class, when we shifted the index to get the same power, we also ended up getting the same index. Is that going to be?
So that's not always the case.
Okay.
So in general, you want to deal with them one by one, but you probably want to follow the pattern that we did in class. First fix the powers, then worry about the index second. Okay. Sometimes you might shift it, and they might all end up starting at the same point, but sometimes you might not. So fix the power first, that's the most important thing. That's going to allow you to combine all terms. And then we also, the next important skill.
You shift the power, and then your indexes aren't aligned, and you have to shift the indexes. Doesn't that change the powers?
No.
What do we have to shift the indexes?
No, because to shift the index, you do it by evaluating terms. You don't actually do it by changing the formula. Which is the third skill I want to remind you of, how we can actually shift an index versus a power. So lastly, the next thing you might recall is the shifting, or maybe I should say changing the starting point. You can do that. Right. So if I have a series where n starts at some value, we can start the series at some future value. Say a plus some integer, right? So I don't want to start at a, I want to start at something further down the line. That is definitely doable. All I have to do is evaluate all the terms before that point. So we can notice that if I have a series I can just evaluate it at a. It's probably a bad thing to try here, but that would look like a sub a x minus x naught a plus a sub a plus 1 x minus x naught to the a plus 1, and I can continue this until I get a to the a plus k minus 1 x minus x naught to the a plus k minus 1, and then I can start the series from k plus a plus k. So I just evaluate the first few terms ahead of the point where I want to start at, and then start the series from there. So yeah.
I'm sorry, so those numbers are not part of the series, right? That if we're going to be evaluating and adding stuff, the ones that we used to get up to where we wanted to get up to, those we just throw away, right?
No, we don't throw them away.
So
They do have to obey something. They do have to obey some formatting.
Okay.
So we'll actually do an example where we actually end up with having to do that, and you'll see how we deal with having these extra stragglers around.
Would that be the initial values?
Huh?
Would that be the IDPs?
That will not be the initial values. So also recall, your initial conditions. It turns out that your the first term in this series, your a sub 0, this is actually going to be your function evaluated at that's going to be the initial condition for your function. And your a1 is going to be the initial condition for the first derivative of your function. And basically, if you pretended your y looks like that, if you plug in n equals 0, which gives you the first term a sub 0, you'll notice that that is actually, if I were to write this up, remember, this is a power series, and this is going to be useful. It's just a0 plus a1 times x minus x naught plus a2 times x minus x naught squared plus, and it keeps going like that. Notice that if I plug in x equals x naught, everyone dies except the first term, a0, right? So y evaluated at x naught is a0, right? So the first term is actually the initial condition evaluated at the point where I'm centering the series. And if I were to differentiate this, y prime, well, that would look like a1 plus 2a2 x minus x naught plus da da. And now if I plug in y prime at x naught, everyone else is going to die, and my a1 is going to be left over. So it turns out the a0 and the a1 are my initial conditions, and in general, we want all other a's a-n's in terms of this. At least for solid. So we looked at second order in your differential
If
equation.
we're doing higher order differential equations, don't we still need initial conditions that are one less?
Yeah, you'll do more. So it turns out that your y double prime would actually be 2 times a2, right? Because when you differentiate the series, right? So you end up with a factorial relationship. The higher up you go, the more they start to look like the coefficients from the Taylor series. But yeah, but for a0 and a1, we're doing second order, and I don't think we go higher than second order, but yeah, so a0 and a1 is your initial conditions. You can always think of those as that. And last time we did an example where we didn't say what a1 and a0 were, but we could write the solution as a0 and a1. So they ended up being like the c1 and c2 from our arbitrary solution. And we could solve for them later if we are given information. Okay, so I think that's pretty much a recap of what we did last time. So a lot of this class is going to be about just doing some more examples, seeing how these ideas apply in a few different contexts. And then we'll move on to talking about singular points and Euler's equations. And at that point, we'll probably run out of time. And we'll deal with a different class of series solutions by next class. So that being said, let's just jump into it. That's a recap. Where was the last part? I wrote up there last time. So let's jump right into another example. Hopefully that little refresher did you some good. So suppose, y double prime minus xy prime minus y equals 0, set x naught equals 1. Find two linearly independent solutions, y1 and y2, to the ODE as series centered at x naught. Suppose y of 1 equals 2, y prime of 1 equals 1. Find the unique series solution. Minus 1. Let's just do that. Do you know how to do that without series?
We should.
Huh?
We should.
You should?
Yeah, we should know how to do it.
Why?
It seems blatantly obvious, but I can't put my finger on it.
What technique would you
You
use?
can't do substitution. You can't use characteristic equation to factor it. Can't use substitution again? No. Because what do you use
Is
substitution
it
for?
Bernoulli?
Well, let's see. Let's find the series solution. If the series happens to be totally blindingly obvious, we'll know, should have seen that coming. If it's not, we're going to be like, oh, this little bugger tricked us. So let's actually jump into that. What would we assume our y looks like?
Absolute convergent series. Sum from 0 to infinity. A to the n, a sub n, x minus x naught, raised to the nth power.
Which is x minus 1 raised to the nth power. So that is how we'll assume our solution will look. I want it centered at x equals x naught. X naught here was given as 1. So,
You guys first, sorry.
What theorem allows you to assume that this is absolutely convergent?
no, there is no theorem that tells me to assume it's absolutely convergent. It's just like what we've always done. We're guessing.
And it works.
We're hoping that a solution like this,
equations.
that's how you do it. Like you pretend, this is my hope that there is a series that's absolutely convergent that solves this guy. Now, once you actually find a series that actually works, you're like, phew, existence and uniqueness theorem, bro. Like you just say that after the fact, right?
How did you assume the form of the series?
Oh, well, it's a power series because I know how to do it. It's just a nice series to use. Why not assume it looks like?
Okay, so we could have assumed that it looked like another series too.
Sure. We're going to do Fourier series, which is a whole other kind of series.
Okay, and you can come to the same answers using different kinds of series.
Well, yeah. If the coefficients are continuous and you're on the interval where they're continuous, then yes, existence and uniqueness theorem tells me no matter where you start, if it pans out, it'll end up being the same thing.
Okay.
We basically choose series based on convenience. There are going to be times where a series of one form is more convenient than another. But here, a series like that seems perfectly. No need to think any harder than that. So, our derivative. And I can start this at 1 if I want, and my y double prime is equal to n equals 1 to n equals 2 to infinity of n times n minus 1 x minus 1 to n minus 2. by the way, I will say the following. See this set of stuff here, in general, don't need to write. I would literally just write these guys, write them in on the spot in the equation. Don't waste time. It's kind of like how when we have a second order linear differential equation with constant coefficients, we just immediately jump to the characteristic equation. I don't show you, oh, we pretend y was e to the rt, and then we differentiate them, then we plug them in, then we try to do that stuff. We set this equal to 0, we end up here. No, we just jump here because we know what it's going to look like. So I wouldn't waste my time writing out this set. Just if you know that's what it's going to look like, just put it here, put it here, put it here right away. Just you don't really need to write this. Just that this is literally the second time we're doing this, so I'm writing it out, but you don't have to write it out. Eventually, you should be able to get used to this to the point where you can just immediately jump to the next line that I'm going to write. Because you know how Jhevon is, his tests take forever. Wherever you can cut corners, save a little time, you do it.
Yes.
You can't tell if that's sarcasm or?
Okay, so what we would do is immediately we would jump into, this is going to look like, see, from 2 to infinity, n times n minus 1, an x minus 1 to the n minus 2, minus x times a series, n a n x minus 1 to the n minus 1 to infinity, minus the series of a n x minus 1 and 0 to infinity equals 0.
Can we just use that shorthand as we write n equals?
Sure. Okay, now what do we do?
Fix the indices. N is equal to 2.
Or we set them on the n equals.
There's an issue though, first.
I should find a middle ground.
Even that guy.
Ignore it.
You can't ignore it.
You can move that inside of x minus.
We want to move it inside, right? We want to be able to multiply it into here.
Yeah.
But how can I actually do that?
Could you substitute for x naught? Would it change anything?
Come again? That's also something, I don't remember if we did that last time, but that's something you should know that you can do. So if you have, say, x outside of a series a n x to the n, in general you can move the x inside and bump up the power by 1, right?
Yeah.
You can actually multiply the x, because the series, according to the series, the variable is n. So your x is kind of like a constant with respect to the series, you can multiply it in and out. How do I get an x to multiply by that? X minus 1.
Wait, just one quick question.
Yes.
Since x is equal to x naught and x naught is equal to 1, can't you just plug in 1?
Plug in 1 where? I already did plug in 1. The 1 is right here. That's my x on.
No, but you see how you go to the ODE as a series center is x is equal to x naught.
Yeah?
Could you just, since x is equal to x naught is equal to 1?
Yes. Correct. And I plugged it in. X naught is equal to 1.
No, but for the outside.
The x coefficient, the x in front of the series is like, why can't you just put that as a 1? The green circle?
That would make all the x's.
Because it's not. It's kind of like, remember back in Calc 1 where it's like, here's a function. Find the equation of the tangent line when x equals 1. It doesn't mean x is always 1.
They
Right?
told us to come
The x can be whatever, but you're just focusing on one point. So there comes a point where you have to treat it as a formula, and then there comes a point at the end where you plug in the number. It's kind of like the same thing. I can't just plug in x equals 1 everywhere.
You could rewrite that as x minus 1 plus 1, and from there you could do something.
Yeah, we can do that. Yeah. I can write this x as, say, x minus 1 plus 1. Why? Because my variable is x minus 1.
That's pretty
So
easy.
now you can
So now I can multiply this in, bump up the power by 1, This is just going to copy the series again. So ultimately, I can go in here. And sometimes, this is kind of annoying to write down all the time. Sometimes what you could have done from the very beginning is you could set, say, z equals x minus 1. So this would mean that your x is equal to z plus 1. And then you assume y is equal to the series of a and z to the n. And then you can go in and you can plug it into this form, y double prime minus z plus 1, y prime minus y equals 0. And then it'll be easy to see that the z will just multiply out. But that's just a shorthand if you don't want to write it out. Otherwise, you can just actually just extrapolate the variable that you want. But you could also just do that, solve for the answer in terms of z, replace z with x minus 1 at the end, and you would be good there. But for now, let's just actually jump into this. So this would look like minus the series of n, a, n, x minus 1 to the n, because that bumps the power up by 1, minus n, a, n, x minus 1 to the n minus 1, minus so this starts at 0. This starts at 1. Okay, now what?
Move the power all to 0.
We want the powers to be the same, right? So I want everyone to be to the nth power. These two guys are good. Those two guys are out of line. What can I do? Can shift with these. So how do I want to shift this one?
And
Shift them all to n plus 2. So I'm just going to add 2, so all the n's, that'll turn this power to n. This one here, I'm going to shift all the n's to n plus 1s. The other two I'm going to leave the same. So once you actually clean up everything into just a sum of series where there are no coefficients except constant coefficients, you focus on the powers. First step. So this is going to be, now remember this is an n equals 2, so if I replace that with n plus 2, I can subtract 2 from both sides. This now starts at 0. And then I'm going to replace every n with n plus 2. So that guy will be at n. Then this guy goes fine. This one, all n's would be replaced with n plus 1, so he now starts at 0. And I have n plus 1, a n plus 1, x minus 1 to the n minus this guy's prime. Now what?
the second one, move it to 0, the lower bound.
Now I'm going to worry about the indexes. So the indexes will be the next quote. What's indices?
Professor,
Yeah,
how does the plus 1 not get distributed? Can you explain that part again?
plus 1 where?
X minus 1 plus 1. Like if you're distributing it, I get the x minus 1 part. But what about the plus 1?
It's right here. That's this. When I multiply this out,
Oh, okay.
it bumps up the power. Then I take the minus 1 times this, gives me minus that.
Okay.
Now, how can I make the indexes the same? Indices.
Make them all 1, and then evaluate each of the other terms in 0.
Just make that 1 by 0.
Make these, evaluate the first term of all of those.
If you know the 0th
Sure, we could do that. There's an easier way.
we know the 0th term of the second series is 0, the 0.
Yeah, I can literally just change this to 0
No.
without changing a thing, right? Because my n is 0, it doesn't add anything. So I can just pretend that starts at 0 and we're good. So then that means I can combine everyone into one big series starting at 0. And this will look like a bunch of stuff times the x minus 1 to the n equals 0. What is that bunch of stuff? Well, I would have the n plus 2, n plus 1, a n plus 2. I would have the minus n plus 1, a n plus. No,
It's minus
these
n.
are that. N plus. I think I want more space. Right, so we'll do. Didn't need a lot of space. Okay, so we got the series of n equals 0. Squinch them up in there. N plus 2 times n plus 1 times a n plus 2. And that's this guy with minus n a n. And that's that guy. We have minus n plus 1, a n plus 1. That's that guy. And then we have a minus a n.
How we set
Now remember over here what we have is the series of 0x minus 1 to the n. Which means for equality, we need this equal to 0. This means that is going to give you what we call
recursive?
the recursive formula, the recurrence formula, the recurrence relation. You have a lot of stuff that start with re. Whatever you might call it, there are many names for it. But it tells us how to recursively or recurrently find the coefficients. Now, again, because I want to save on writing time, I'm just going to solve for what I need to solve for right away before I write it down. So what do we normally solve for?
The highest index.
The highest index, which means ultimately I'm going to want to solve for the a n plus 2. That's the highest index, which means I'm going to take all these guys, move it to the other side. So notice I'm going to have n plus 1 times a n, and I'm also going to have n plus 1 times a n plus 1. Right? Because I have the minus n a n and minus 1 a n, that's minus parentheses n plus 1 a n, move it over, that's that. And then this guy is going to be the n plus 1 a n plus 1. Notice then that the n plus 1 is a common term, so I can just factor it out. Over the coefficient here. So that's n plus 1 times n plus 2. These guys will cancel. So then I have my a n plus 2 is just a n plus 1 over n plus 2. This is what's called the recurrence relation. And that's the guy that tells us how to find the coefficients. So I'm just going to start plugging them in.
What is the recursive, what does the recurrence formula show again?
It helps us to find the coefficients, the ANs.
So you did all of this just to find coefficients.
Yes, that's the point, yeah. This was the whole point.
How did you factor out an n plus 1 in the top?
Because it was a common term. I had n plus 1 times an plus n plus 1 times an plus 1. So n plus 1 is a common term, you factor it out.
Up there, I thought you had n times an only.
No, there's another an right here.
Oh, okay. Okay.
Right, there's an an here. There's a minus an and there's a minus n. Right, so there's an n plus 1 an, which was negative, and then I moved it over, it became positive. Okay, so remember, our A0 and our A1, they're just themselves. They can be whatever. Now I want to find the A2s and all the other guys. Right? So how do I find A2s? Well, I go to the recurrence relation, and I'm going to plug in, say, n equals 0. Now That means plug in 0 here, that gives me A2. That will give me A0 plus A1 over 2. So that's going to be A0 over 2 plus A1 over 2. Then I can plug in what's A3. Well, for A3, I would plug in n equals 1. And I would get A1 plus A2 all over 3.
If we write A2 is,
And this is A1 over 3 plus A2 was this guy. So that's going to be A0 over 6 plus A1 over 6 plus, which is going to be equal to A1 over 2 plus A0 over 6. Dot, dot, dot. Now, normally, especially if it's not going to be anything nice, I'll tell you how many terms I want right here. I'm kind of bored, so I don't want any more terms of this.
14.
So, what is this going to actually give us? So, we're going to go in. We now know our y is equal to, well, we assumed that it was this. But what is that? Well, this is A0 plus A1 times x minus 1 to the 1 plus A2 times x minus 1 squared plus A3 times x minus 1 cubed plus dot, 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 keeps going. Now what you'll realize, A0 and A1 are themselves. For the A2 is going to split into 2 parts. So I'm going to have an A0 over 2 times x minus 1 squared plus an A1 over 2 times x minus 1 squared plus the A3 is going to split into 2 parts. That's an A1 over 2 x minus x1 cubed plus an A0 over 6 x minus 1 cubed plus dot, dot, dot. Now,
So again, when we have higher order differential equations, we're gonna have like A1 or A0 with a bunch of terms, and then A1
with a bunch of terms, and then A2 with a bunch of terms. If
A
you're,
with a bunch of terms.
yeah. But you solve for everyone in terms of pretty much A sub n, where n is the order. A sub n minus 1, where n is the order. Okay, so for a second order, I need to get up to A1, needs to be given as an initial condition. For third order, A2 needs to also be given as an initial condition, etc. How do you find the 2 linearly independent terms? Well, you separate the A0s and the A1s pretty much. So A0, what's attached to A0?
1
Well, 1
half x minus 1
plus a
squared.
half times x minus 1
Squared.
is x minus 1, right?
Oh, squared.
Squared. Then,
Half x minus 1
1
cubed.
6.
Oh, yeah, 1/6 x minus 1.
X minus 1 cubed.
and plus A1
X minus 1. X minus 1. Half x minus 1 squared. X minus 1.
where?
Half
X minus 1 squared.
That's it.
And then half x minus 1 cubed, which is
This looks familiar?
yeah, obviously.
This?
Yeah,
We have both of them.
Yeah, did you study calculus?
yeah, come on.
What does it look like?
You know.
You know, you should know.
Sine,
It's easy.
Teacher.
You should know this.
You guys are hanging around me too much. Like, you guys don't know this? Yeah, that's the series. Well, I kind of felt like I knew this, you know, oh, it's denominator is 1 factorial and 2 factorial and 3 3 factorial, then it's like, that kills any hope of me recognizing that now. But this guy kind of looks like an exponential, right?
Kind of.
And
Pretty
this,
sure Bernoulli described all of this. One of them.
yeah, so one of the Bernoulli, yeah.
It's like the secondary Bernoulli.
You guys really are. Okay, so those are our 2 solutions, and we found them as series. At least we found the first 3 terms because we got through.
So when you ask for an answer, you're going to ask us for
Yeah, I'll give you the
series,
first
just
number of
certain
terms.
number of terms.
Yep.
And how do we solve for A0 and A1 given the conditions?
Okay, so now we were given, so this is part B really. We were given that at 1 we had 2, and y prime of 1 we had minus 1. Right?
Yeah.
So, but notice what that means. This guy here is actually just A0, and this guy here is actually just A1. And the reason why is, if my y was A0 plus A1 x minus 1 plus A2 x minus 1 squared plus A3 x minus 1 cubed plus blah, blah, blah. Well, then my y prime would be A1 plus 2A2 x minus 1 plus blah, blah, blah. Notice here, if I plug in 1, these will all die. A0 is going to be that number, but they told me that was 2. And if I plug in 1 here, these will all die. I'd be left with A1, which they told me is minus 1. So those guys are actually my initial conditions. And so this implies that our y is going to be 2 times this. Let's try this 2 times 1 plus minus 1 times this.
Can we still subtract like the series?
Huh?
Can we just distribute the 2 and distribute the 1 and then subtract?
You could, but because of the way the question was phrased, I'm keeping them separate. Because the question specifically mentioned y1 and y2. So I keep them separate as y1 and y2. So this is my first solution, this is my second solution, and these coefficients is just to make me get the particular solution. So this is like your y bonus round.
So, I'm sorry.
Yes.
Why do we have to find y again? And what's this process for again? I forgot.
To solve the differential equation.
Alright.
Right, we started out with this guy, with 0. I want to solve that. Can you think of a better way?
Let's say.
What makes that, like, is there a name for that kind of differential equation? With the x thrown in
This
there?
one specifically, no. But we are gonna have some where they have names. That it's gonna be like, because they show up all the time.
So is this the only way to solve this one other than another series?
I can't think of a method off the top of my head that I told you guys about. I didn't tell you a method that would do this.
Okay.
So,
So this is the way.
in 391, this is how we do it. Bonus. I would usually prove that they're linearly independent.
Show that the things repeat.
Vronsky.
How do you think that's
How do
fine?
you do it? The Wronskian. So,
It's gonna be fun.
what is the Wronskian?
Oh, you have to do the differentiate the series term by
It's a
term.
cross product.
That's the thing.
So if you look at the Wronskian of y1, y2, what does that look like?
The determinant of y1, y2, y prime, y prime.
Right, so it's y1, y1 prime, y2, y2 prime. So that's going to be y1, y2 prime minus y2, y1 prime. So what does that, right, we want it to not be 0. So I'm hoping if I do this with that, it's not going to be 0. So what is y1 prime? What is y1 here? Well, I would just plug it in.
I don't know, you have to do it anyway, so. Might as well, right?
Y2 prime, what is y2 prime?
X minus 1.
Wait, Y2 prime or just Y2?
Y2 prime.
Wouldn't that be x minus 1?
No, I'm going to be differentiating that.
Oh,
Yeah,
okay.
because you can
So it's
second
going to
could
be
be
1
1 plus
the first one,
1
then
plus x minus 1.
plus
1 half.
x minus 1 plus a bunch of stuff. Actually, you don't need to know that. Y2, just x minus 1 plus 1 half x minus 1 squared plus da, da, da. Plus times
X
y1
minus
prime
X minus 1 plus half x minus 1 squared. Now you factor.
now.
Oh, that's just that thing squared. The second thing.
So remember, we just want to know that it's not 0 at the point, at some small interval around the point. So I can literally just, what does the Wronskian look like at 1? Well, I can plug that in. This will be 1, because all of these would be 0.
What?
And this will be 1, because all those will be 0, minus.
0.
These will all be 0. Those will all be 0. So it's 1, not equal to 0. And so they're linearly independent at the point.
How do you show it's linearly dependent at all points? Or can
Well, I multiply this out, get a general polynomial, and just show that that's not going to be 0 for these x values. So needless to say, these guys can take a while. That's just...
That was like an hour.
for one problem with all your shortcuts.
What?
How do you write really fast?
We could just pick one for the last thing. Could you pick any number we want?
Well, no, the power series is centered at 1. So in
Okay.
particular, I just want to know it works around the point centered. So let's actually do... So this one is actually from a past final. Cool thing about these problems is I can give you the solution and you're not going to remember it anyway. So it's not- when you go into practice final again, you're never going to remember that we actually did this. Look at all this.
You gotta show us all the organizational tricks for these.
There's I just did it. So okay, so here's an example. This was actually on fall 2014. 2011, problem 4. So it gave us this 3 minus x No, there's another method we're going to learn. We're also going to learn another kind of series method altogether. We're going to learn another method to deal with certain equations. And want to learn anything more complicated? Take a graduate course, I guess. The good thing is in application-wise, engineering and that sort of thing, usually if your differential equation doesn't look like one of the things you learned to solve in this class, there's going to be a method to approximate it with a differential equation that you would find in this class. So you kind of you can always reduce your problem to a very simpler one. Okay, so this specifically said find the first 4 terms. So it says compute first 4 terms of the series solution centered at x1. With y of 0 equals minus 6, y prime of 0 equals 2. So I mentioned earlier that our differential equation can dictate the an upper bound for the radius of convergence. So let me add a problem here.
Where the series is centered is always going to be the value we plug into our initial conditions.
Yeah, because that's where you know how things are behaving. What is that integral where the solution exists? Maybe large as possible. Because you have to really find the radius of convergence of the series to know for sure. But okay. So, what is the series solution going to look like?
We're gonna skip the first step.
Yeah.
Plug in the
So our y equals the summation of a and x to the n, right? Because it's x minus 0 to the n, right? So we are going to get 3 times n minus 1 a n.
Wait, why isn't 3 minus x?
So that'll be the next one.
N minus 2 minus n minus 1 a n x to the n minus 1.
Wait. Why is the first coefficient not 3 minus x?
Because that's the second
It's
one.
3 minus x. I'm plugging it all in.
Oh, you distributed that. You have to
I
distribute
already
that.
distributed, yes.
Okay.
So, I realized, this is 3y double prime minus xy plus x y prime plus y plus xy. Right, so the 3y double prime is that, the minus xy double prime is that. And it's going to be from 2 to infinity, 2 to infinity. I mean, I'd write an extra line, but Chris was like, "Ooh, show us some organization." This is how I would do it. I would just not write.
Just not you have
I would just not do a bunch of these lines where I'm expanding. Like, you know how to expand. You know how we got here, right? You're just kind of
I appreciate it.
right. Plus, then you're going to multiply them by x squared. So the derivative is going to look like n a n x to the n minus 1, but I'm going to bump that power up by 2, so that's x plus 1. And this one I can start from 1 to infinity.
Wait, go back really quick.
This is x to the n minus 1, because that's the first derivative. And I multiply by an x squared.
Okay. I
So
got
the
it.
power becomes n minus 1 plus 2,
Okay.
which is an n plus 1. So that's this guy. This guy is just going to be y plus a n x to the n, starting at 0, plus a n x to the n plus 1, starting at 0. All of that equals to 0. Okay, so now, get all the powers the same. So this is going to be, I I'm going to shift all the n's to n plus 2s.
We want to always make the powers an n.
Yes.
I don't know. It's just
So I shift all n's to n plus 2s. I can move the 3 in here. So I'm going to shift all these n's to n plus 1s. So this one is going to start at 1. Shift all these guys to n minus 1s. So this series is going to start at 2. This guy doesn't need to be shifted. Shift all the n's to n minus 1s. So this is going to start at 1. And all of that equals 0.
I'm sorry, so you said the first term doesn't need to be shifted, which I get. but
So
why
this
do you-
term needs to be shifted. I change all n's
Oh,
to
I'm
n
sorry,
plus
there's a whole
2.
other line. Shit.
Yeah, this is, it's one line that I'm
I
writing.
need wider
in two
paper.
lines. Yeah, I need a wider report. This is one line. And then this is the other one. So these problems are basically to test their concentration. You know, if you like go off to a mountain to live with the monks, there's that day where they like have you stand on the pole with one hand. Like that's what this is. This is that part of the course, which is it's all about can you focus.
It's actually only in Japan.
It's only in Japan they do it. Okay, so all the parts are the same. Can we get them all to start at the same?
Yeah, they already are.
Well, no, there are some at zeros, there are some at ones.
Yeah,
There's
but it doesn't
at
matter.
two.
Just 0, you know, except that one.
Zero can work here because that'll just kill itself.
But it doesn't work in the second
You
one.
could plug in 0 and, well, you can plug in 0 for everything, but not 1. Right?
You
Why
can't
not?
plug in 0 for the second index, the one where I was index is 2.
We can plug in 0 here, no problem.
But not here.
Can we plug in 0 here?
No.
Why not?
We get a different thing.
What
We get
will
negative
we-
1,
You just get a negative.
We get a non-zero number, so you
Sure.
can't just like
You get a
slap it
negative
on.
in the term.
So you write the negative term, then you add the 0.
I get a sub minus 1, but what is a sub minus 1?
That's
You can't actually ignore it.
Why? Because it's one of the series terms?
If we plug in, maybe I'll justify that later. So let's say we're not going to ignore it, but you can actually ignore it. So there's something called a wrong series.
Okay, you're being devious.
I'm not being devious. So there's a thing. It really exists. I'm not making this up. But it's possible to count a series in both directions. So you go from n equals minus infinity to infinity. Right, so you can literally, he's laughing like he doesn't believe, it's a thing, for real. So you can have like this, and it would go like a0, a1x, a2x squared, a3x cubed, plus dot dot dot, and you can literally go backwards, a to the minus 1, x to the minus 1, a to the minus 2, x to the minus 2.
That makes sense.
and the
Right?
sum
You
is
can
just,
generalize a series like that. So the thing is, if we think about our series in this context, what would all of these guys have to be? Well, they'd have to be 0 because we're only assuming that it looks like from here onwards.
Oh, okay.
So you can automatically just assume if I get a to a negative subscript, they're all 0 because I'm not assuming they're a part of my solution anyway. My solution is assumed to look like this.
So it could be optimal to get a negative subscript.
There are times when you would need the negative subscript. In fact, in complex analysis, it's super important to be able to get that negative subscript. In particular, this negative subscript is super important in complex analysis. That guy is more important than everyone else in the series.
I thought we said n had to be a natural number. We do get I mean, like
For sequences, sure.
okay.
But yes, I'm really generalizing here. But let's actually just continue. Let's, I guess, pretend that we don't have to do it, and then I will tell you that we can, maybe next time. Okay, so we're not allowed to actually move things back down. So what do we do then?
Move it all to 1.
Right now, that's it.
I can pretty much, what I'm going to do is I'm going to evaluate a bunch of terms, but eventually I'm going to want to be able to start all the series at 2. Start them based on the biggest guy, right? So now if I get all of them to start at 2, this would be 3n plus 1, n plus 2, an plus 2, minus n times n plus 1, an plus 1, plus n minus 1, an minus 1, plus an plus an minus 1, x to the n equals 0. Now, how can I justify doing that? Well, what I'm going to do is I'm going to evaluate some of the terms from the guys that didn't start at 2. What would I end up with if I do that? So, this guy didn't start at 2, he started at 0. So I'm just going to plug in n equals 0. What am I going to get?
6an
6a
2.
x to the 0. Then if I plug in 1, right, so if I plug in 1, that's going to be 2, that's going to be 3, that is 2 times 3, which is 6, times 3.
No, it's 18.
It's 18, a 3x, right? So that's the first 2 terms evaluated there. Okay, I need to evaluate 1 from here. So I plug in n equals 1, what do I get?
2n
2, a2, x. Now, I also need, this guy's fine, he's already at 2. This guy, I need to evaluate 2 of him, right? So there's going to be a plus a0 plus a1x. I need to evaluate 1 of these guys. So that's going to be a plus a0x, right? Plus this whole series. Now, this part is actually what? What is this? Like, let's group these guys. What are the constant terms?
a0, 1, 2, 3.
Huh?
a0, a1,
A0 and
There's another A0 over there. A0.
That's not a constant.
it's not a constant here. Plus 6a2
That's it.
plus all the x's.
18a3. 2a2. a1. a1 and a0.
Plus a1 plus a0 times x. Do you have anything bigger? No. Okay, so here's what we will actually have. I will be able to, well, let me do this first. So we're going to set this whole thing equal to 0. We'll worry about those guys later. And this equal to 0, put that in blue. What would I solve for here?
an plus 2.
an plus 2. What would that look like? Well, it would look like a bunch of stuff divided by 3n plus 1, n plus 2. that bunch of stuff.
Positive n plus 1, an plus 1.
Yeah. Minus n minus 1, an minus 1.
You can cancel that out.
Can cancel what out?
An minus 1.
Yes, so an an minus 1 goes away, so I just have what? N an minus 1 minus n an minus 1. Okay, so I got it. All right,
Wait,
let's
can we
go.
cancel the an minus? Actually, never mind. No, we can't.
The middle term?
Okay, so what do we know so far? We are told that our A0 is equal to minus 6. We're told that A1 is equal to 2. So, I'm now going to plug in.
So are we gonna worry about the green?
In a little bit. So, how would I find A2?
Plug in n is 0.
Plug in n equals 0. What would I get here?
0 minus a of n, a of 0.
A of negative 1.
So minus A0 over
6.
6.
Yeah.
No,
Wait, where's the?
no,
is
it's
zero?
over 8, it's over,
Times 1 times 2.
Oh,
yeah, it's over 6.
Over 6.
Yeah.
Okay, now. Check this out. This has to be 0. All the coefficients on that side have to be 0. How many constants are there over here? 0 constants. How many constants are there over here? Well, A0 plus 6, A2. That has to be 0. If that equals 0, what would A2 be? Minus A0 over 6. Turns out that the recurrence relation that I figure out here will actually cover all the terms that I have here.
That's crazy.
Which is kind of another reason why, yeah, I could just ignore that. When I was talking about, we could just ignore that stuff, because all the stuff that will be generated by me having to worry about, what if I have a negative subscript? I pick them up all at the end with the recurrence relation. It's still, this guy is going to, these guys will have to still obey that formula. So, here, what you'll notice then is I kind of have an option. I can either find my A2 and my A3 from the recurrence relation, or I can literally find my A2 and my A3 from this thing that I already worked so hard to generate in the first place. Right? They'll both give me the same answer. If I set that coefficient equal to 0, that's going to get me my A3. Now if I have A0, A1, A2, A3, that's 4.
I have a question.
Yes. What was A0 again? I already said.
Negative 6.
Negative 6. So this will be
1.
positive 1.
Oh, yeah.
Right?
Okay.
My A3, what is that going to be? Well, I can use the recurrence relation, or I can set the coefficient of x to be 0. That means it's going to be minus A0, minus A1, minus 2A2, all over 18. And you'll realize that that will actually match the recurrence relation if I plug in n equals 1.
Sorry, can you say that last part again?
Well, to do this, what I was looking at was this coefficient of x over here. The 18A3 plus 2A2, blah, 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 blah. That coefficient has to be 0. So if I set it equal to 0, solve for the A3, I'm going to get this. And what I said, if you plug in n equals 1 here, you should get the same thing. And what was my A1? My A0 was minus 6, so that would be plus 6. My A1 is 2. My A2 is 1. All over 18. So this would give me what?
1 over 9.
2 2 over 18, right? Or 1 over 9. And in fact, those are all the terms I need. We only have to find the first 4 terms. This implies our y is equal to the sum of from 0 to infinity of a n x to the n, which is approximated by us to be the sum of the first 4 terms. Which is that. My a0 is minus 6, my a1 is 2, my a2 is 1, my a3 is 1/9. So my solution approximately behaves like this to the first 4 terms.
Which formula do you use for A3?
I can use either. I can either use what's in the parentheses in green. I can use this formula, just plug in n equals 1. That will give me a3 here. I can solve for it.
I got
Or
0
in
on
this
it.
formula, if I said this equal to 0, because it better be 0, I can get that that way too.
Because 0 plus 0 has to be 0, right? That's why.
Because 0 plus 0 has to be 0. That's very well said. 0 plus 0 has to be 0. Did they ask anything else?
In
The
general,
boundaries
you
of the
something about
infinite.
So that would be the answer here.
No,
How did,
That's for the highest possible value for some boundary. Yeah, the highest.
yeah, so this is a solution. How do I know what interval this solution will work on?
Negative or positive infinity because of
Well, what was the original equation again?
3 minus x, y double prime, plus x squared, y prime, plus 1 plus x.
Now, remember how we define where a differential equation has a unique solution by the existence and uniqueness theorem? We first found the standard form, right? So notice that what will happen is I have to divide through by the 3 minus x. Which means our x cannot be 3, right? So where is our initial condition? Our initial condition is at what? At 0. This means if we're on the interval, on the real line, we are here at 0, but at 3, that's bad, right? The world ends right here. Which means, how big can this power series actually get? 3 units long. The radius of convergence is at most 3.
Is that an actual radius? Or is it just like a metaphorical radius?
No, it's a real radius. Like on the other side, the function might be completely different.
Okay.
However, on that side, on the interval between minus 3 and 3, that's your unique solution.
So that's why it's a radius.
So that's why it's a radius. Because
Okay.
it depends. Remember, the unique solution depends on where the coefficients are continuous.
So the interval is between -3 and 3.
Why can't it be negative 3?
Huh?
Why can it not be negative 3?
It can extend all.
Negative infinity?
Well, I don't know for sure, but at most it can extend up to here or back there, because power series unfold into a radius.
It can't be
right?
negative infinity?
No,
Because then it would run it on the other side of it.
because it would have to extend here.
This is the radius.
But radiuses don't have to be symmetric.
Yeah, they do.
For power series, they do, yes. You find the radius using the ratio test. Remember, it gives you an absolute value less than something, which it spans out into the negative thing and the positive thing. So your radius is always going to have a limit.
Like, I got a brush up on that.
Yeah, brush up on it. The radius has to, the interval has to be symmetrical around the point where it's in.
Chapter 5.1 of the book, that's using the ratio test to determine the
It was
radius.
supposed to be,
Yeah, I'll probably put some homework plans on that. But.
oh, okay.
It has you determine, just like take questions.
So we will stop there. So one question you might ask is, what if x is actually equal to 3?
Might be helpful.
Yeah.
Can we actually talk about that point? And it turns out, yes. But that is 5.3, I want to that
I
next
think
time.
this is all just 5.1.
No, I'm pretty sure we're in 5.1, right?
Not 5.2 has to do with.
No, we're in 5.2, right?
We're gonna catch up.
But we'll stop there.
Thank you.
excuse me,